Hi dear students, welcome to the last topic of this module, aromatic hydrocarbons, and today's module topic is aromaticity. At the beginning of this module we have learned that aromatic compounds are characterized by their special stability due to resonance. Conjugated cyclic compounds like benzene, toluene, naphthalene, etc., they are having alternate single and double bonds, and they are characterized by complete cyclic delocalization of pi electrons, that is due to resonance, which make them specially stable. They resist addition reaction, instead undergo substitution reactions, which we have seen in detail in previous classes. And this unusual stability is what is called aromaticity. Now, regarding how to predict whether a compound is aromatic or not, we have a rule called Hackle's rule, which originates from quantum mechanics. Based on quantum mechanics, we have learned a theory called molecular orbital theory, and it is from this theory Hackle rule emerges. What is this rule saying? It states that a planar cyclic conjugated polyene will be aromatic if and only if it contains 4n plus 2 pi electrons, where n is 0, 1, 2, 3, etc. So substituting the value of n, we get Hackle numbers as 2, 6, 10, etc. So in Hackle rule, we can see that there are mainly three conditions for a compound to be aromatic. That is, number one, it should be planar. Complete planarity is required. That is required for resonance to occur. Because, for example, if you take benzene itself, we have learned the structure of benzene in detail earlier on. You know, in benzene, the pi bonds are formed by the lateral overlapping of p orbitals, and the p orbitals are placed perpendicular to the plane of the ring. So we can show them like this. These are the p orbitals perpendicular to the plane of the ring or the sigma skeleton. Okay. And all the carbon atoms in benzene are sp2 hybridized. So sp2 hybridization is required for the planarity, so that these orbitals can laterally overlap and resonance occur when these p orbitals simultaneously overlap, right, like this. So this make up this complete delocalization. So there is a second condition, complete cyclic delocalization. So when there is complete cyclic delocalization, then we have the compound will be aromatic only when there is complete cyclic delocalization, for which planarity is a prerequisite. So these are the two conditions: complete planarity, number two, complete cyclic delocalization. What do you mean by cyclic delocalization? That means, see, this 3 pi bonds in alternate pi bonds in benzene, due to resonance, you know, we show like this the resonance structures, right, like this. So when due to this resonance, the pi electrons are making a cyclic ring, we call it pi electron ring. This is complete cyclic delocalization. Then only compound will be aromatic. And third condition is, even if the compound is planar and it is having complete cyclic delocalization, still for the compound to be aromatic, it should satisfy the Hackle number. That means number of pi electrons should be Hackle number. 4n plus 2 pi electrons should be there in the compound, where n equal 0, 1, 2, 3, etc. So the magic numbers or Hackle numbers are 2, 6, 10, etc. That means if the compound is having 2 pi electron or 6 pi electrons or 10 pi electrons, etc., then only it can be aromatic. Let us now go to examples to illustrate this. First we consider benzenoid compounds, that's benzene-like compounds, compounds containing benzene rings. The first one is monocyclic compounds, that is benzene only. It's very clear. It has complete cyclic delocalization. It is planar because all carbon atoms are sp2. And if you apply Hackle rule, 4n plus 2 rule, here n equal 1. So 4n plus 2, that means 4 into 1 plus 2, that is 6 pi electrons. Because there are 3 pi bonds, so it is equal to 6 pi electrons. So benzene is aromatic. It's very clear. And if you think how this Hackle number comes from, where from it comes, I have already told you it is based on molecular orbital theory. In the discussion of structure of benzene, we have already learned that in the molecular orbital diagram of benzene, if you consider the pi molecular orbitals, there are 3 bonding MOs for benzene and all the 3 MOs are completely filled. So for filling all the bonding MOs, benzene requires 6 pi electrons. So we can say that Hackle number is in accordance with complete filling of the bonding molecular orbitals of the compound, so that it will be extremely stable. Resonance stabilization of benzene is expressed in terms of resonance energy. We have already learned that point also. For benzene it is 152 kilojoule per mole, a very high resonance energy for benzene, indicating that it is quite stable or it is stabilized due to resonance, or it is quite aromatic. Going to the next example, we take polycyclic compounds, that is again benzenoid compounds, or fused ring systems. We know when two benzene ring is fused sidewise, sharing carbon atoms, we get naphthalene. When it can go linear way or angular way, if there are 3 benzene rings joined, fused together, it is anthracene. In linear fashion, if it is angular fashion, it is called phenanthrene. All these are clearly aromatic. If you check the conditions, all the carbon atoms are sp2 hybridized, so it is completely planar. Then there is complete cyclic delocalization, there is alternate single and double bonds, and all are Hackle numbers. For naphthalene, n equal 2. So 4 into 2 plus 2, that is 10 pi electrons, because there are 5 pi bonds. In anthracene there are 7 pi bonds, so 14 pi electrons. It is again Hackle number because n equal 3. So 4 into 3 plus 2, that is 10. Sorry, n equal 2. So 4 into 2 plus, benzene is 4 into 1 plus 2, that is 6. Naphthalene is 4 into 2 plus 2, that is 10 pi electrons. Anthracene is 4 into 3 plus 2, that is 14 pi electrons. Phenanthrene also is the same, 4 into 3 plus 2, that is 14 pi electrons. Going to the next category of aromatic compounds, that is, they are called non-benzenoid compounds. They do not contain benzene-like rings, still they are aromatic. In that, first we consider monocyclic. Here there are some very important examples. The first one is cyclopropenyl cation. See, this is cyclopropane and this is cyclopropene, correct? Is it aromatic? Let us check. Is it planar? See, these two carbons are sp2, but this is not. This is not sp2, this is sp3. So naturally this compound will be non-planar, will be having a puckered structure. So if it is not planar, it cannot have the lateral overlapping of p orbitals properly for resonance to occur. So this is not aromatic, right? Because it is not completely planar. So, but this can be made aromatic by introducing a positive charge on this sp3 carbon. How it is done? See this, there are two hydrogens here, right? If you can remove one H hydrogen from this carbon as H minus or hydride, like this bond is broken in favor of hydrogen, so it is removed as H minus. You can realize it using some very reactive metals like lithium, etc. It will form lithium hydride where hydrogen exists as H minus. So if H minus is removed from here, if one H minus is removed from here, one H will be there and the other is H minus is removed, so there will be a positive charge here, right? A positive charge will be there over here on this carbon. So that means it become a carbocation. You know, carbocation is sp2 hybridized. Now it will be completely planar and resonance can occur. This pi bond can shift to this point, okay, so that you get next structure like this, where pi bond is now here and positive charge appear here, and it will continue. Pi bond now move to this place and it will continue. So that can be shown as this complete delocalization of pi electrons in cyclopropane can be shown now like this. Positive charge put here and we use a broken line ring. This is the delocalized pi electron ring. So cyclopropenyl cation is aromatic because there is only one pi bond, that is 2 pi electrons, and it is a Hackle number, and there is complete cyclic delocalization. Even though there is a charge, it is aromatic. Now interesting example is this one. See, what is this compound? Tell me. This is cyclobutane. If I put 2 pi bonds here, what is this? Cyclobutadiene, correct? You can see all carbons are sp2, so it is completely planar. And there can be complete cyclic delocalization. That means due to resonance, this pi bond can shift to this point, this can shift to this point, and it is completely delocalized. Complete cyclic delocalization is there. Now the question is it aromatic? You now check the third condition, that is whether it is Hackle number. 2 pi bonds equivalent to 4 pi electrons. Is it a Hackle number? No. So cyclobutadiene, even if it is satisfying first two conditions, it is not a Hackle number and it is not aromatic. So it's a very interesting example. Now the next one, 5-membered ring, you can see the example given here. Cyclopentadienyl anion. See, it's not cation, it is anion. The compound is this cyclopenta, 5-membered ring. There are 2 pi bonds here. Cyclopentadiene, this is cyclopentadiene. This is not aromatic. Why? Because it is not Hackle number. But this can be made aromatic, and here it is not by introducing positive charge but introducing a negative charge. Why? If you introduce a negative charge and that will be a lone pair, you know that in resonance lone pair can also participate. N-pi conjugation is possible. So what you do is, from these two hydrogens over here, this is sp3, we can remove one as H plus using some strong base. So if one H is removed as H plus, this bond pair will be remaining on this carbon, so that we can show it now like this. You can see that this is one H here. Sorry, I will remove the bond, and this is one H here, and one H plus is removed, so that will appear as a negative charge here with a lone pair. There will be lone pair. So this is a lone pair, a negative charge. So now this lone pair is in conjugation with the pi bonds. That means this lone pair can now move to this point, delocalized, so that this pi electron will be moving to this carbon, and in the next step lone pair over here will be placed to this position and pi bond will be moved to this place, and it continues. That means there is complete cyclic delocalization here. So this cyclopentadienyl anion is aromatic due to these reasons. We can draw this complete cyclic delocalization of cyclopentadienyl anion like this. There's a negative charge which is delocalized all over the carbons. So this is the structure, resonance structure of cyclopentadienyl anion. It is aromatic. Okay, now you can easily understand all other examples in the similar fashion. The third one is cycloheptatrienyl cation. It's a 7-membered ring. It is also called tropylium cation, a very popular name. Tropylium cation. What is it? 7-membered ring like this. Look here. Okay, it is like this. Okay, I will redraw it. It's like this. Cycloheptatrienyl. So there are 3 pi bonds in alternate position. Okay, but one carbon you can see it is sp3. So it is not completely planar. It will be puckered or non-planar, and complete delocalization, cyclic delocalization not possible also. So what we do is, since there are 3 pi bonds, so 6 pi electrons, it is Hackle number. So we cannot introduce lone pair here, that will violate Hackle rule. So instead, for complete delocalization, we remove one H from this sp3 carbon as H minus and introduce a positive charge here. That will make it sp2, and complete delocalization will be possible due to resonance here. So now this movement will take place continuously like this. It comes here, this comes here. So complete delocalization takes place like this, and it is aromatic. Now we take some other examples here. Again monocyclic, but these are heterocyclic compounds. What is heterocyclic compound? Generally, all these compounds, all the compounds which we discussed so far are carbocyclic. That means only carbon atoms in the ring. There are heterocyclic compounds where the ring contains some heteroatoms like nitrogen, oxygen, etc. Here we have examples: pyrrole, furan, thiophene, pyridine, etc. For example, let us take pyrrole. Here pyrrole is a 5-membered ring with one nitrogen atom. Let us check whether it is aromatic or not. There is one nitrogen here, and there is one hydrogen also here. There are only 2 pi bonds. Okay, you can clearly see 2 pi bonds means it is not aromatic. 4 pi electrons, it is not Hackle number. But since there is a lone pair on nitrogen here, nitrogen has a lone pair. This lone pair is in conjugation with the pi bond, and it can take part in resonance, as you know. So the lone pair will get delocalized to the next point position, and the pi electron will get onto the next carbon, and it will continue. So there will be complete delocalization with the help of the lone pair. So lone pair also is counted as a pi electron here because it is taking place in resonance. So altogether there are 6 pi electrons, 2 pi bonds and 1 lone pair. So 6 pi electrons is a Hackle number. So due to resonance, there is complete delocalization, cyclic delocalization possible here with charge separation, and it is aromatic. So pyrrole is aromatic. Likewise, all other examples like what is shown here, that is furan, where instead of nitrogen it is oxygen, which also contain lone pair, and it is aromatic with the participation of the lone pair. Thiophene, where it is sulfur, there also it is aromatic. What about pyridine? Pyridine is like benzene, except that one carbon is replaced by nitrogen. There is one nitrogen here, and there are 3 pi bonds just like benzene. You know, whenever there is nitrogen, there is a lone pair. What about its aromaticity? Obviously, it is aromatic, just like just like benzene, because 3 pi bonds equivalent to 6 pi electrons. It is Hackle number. All are sp2. There is complete cyclic delocalization. Then what about the lone pair? Lone pair will not take part in this delocalization. It is not required. Even without the lone pair, it is aromatic. So it is aromatic only. Interesting point is, when you compare basicity, basic strength of these Lewis bases like pyridine and pyrrole, you can see that pyridine is more basic than pyrrole. What could be the reason? In pyrrole, the lone pair is used for delocalization, so that it is less available for donation. But in pyridine, lone pair is not required for this aromatic delocalization. So the lone pair is more available in pyridine and it is more basic. So that's a related point here. Okay, now finally we have bicyclic compounds which is also heteroaromatic. First one is quinoline. It is just like naphthalene. Only difference is there is one nitrogen in place of carbon. Obviously there are 5 pi bonds, so 10 pi electrons, so it is Hackle number and it satisfies all the conditions. It is aromatic. Indole. In indole there are only 4 pi bonds, so it is 8 pi electrons. It is not Hackle number, but nitrogen is having a lone pair which is conjugated with a pi bond and it can take part in resonance. So the lone pair of nitrogen will undergo delocalization along with the pi bonds and indole also becomes aromatic. So counting lone pair along with the pi electrons, it is 10 pi electrons, n equal to, so indole is also aromatic with the participation of the lone pair of nitrogen. So that's all about concept of aromaticity, how to predict whether a compound is aromatic or not. Now these are the questions for practice. You should work out all these questions in your notebook. With this, we wind up this module, that is aromatic hydrocarbons. We have one more module left, a very short module, that is alkaloids and terpenoids, something about natural compounds, which is also important part of organic chemistry. Thank you.